Welcome back to the deep dive. I'm so glad you're here with us today because our mission is nothing short of extraordinary.
It really is. We've got a lot of ground to cover.
We do. We are taking this massive stack of historical physics documents, engineering papers, and information theory sources to answer a 147-year-old mystery.
Yeah.
The mission today is to uncover how two entirely different fields of science fields that, on their surface seem to have absolutely nothing to do with one another, turned out to be the exact same fundamental mechanism of reality.
Right. And just to give you a sense of the sheer scale of the landscape we're looking at here, we are going to guide you through a scientific narrative that stretches over 64 years of active debate.
A long time.
Very long. We'll be following a trail of clues left by some of the most brilliant minds in history. It's a puzzle that fundamentally alters our understanding of the physical universe, and the entire thing started with a rather cryptic formula carved onto a tombstone.
Let's start right there, actually, in the cold open. I want you to picture a sprawling graveyard in Vienna, Austria.
The Zentralfriedhof.
Exactly. It's where some of the greatest composers and thinkers are buried. And on one particular tombstone, there is a very brief, elegant mathematical formula carved right into the stone marble.
It reads S equals K times the log of W.
Right. This is the final resting place of a physicist named Ludwig Boltzmann. And that little string of letters and symbols, that was his life's work.
His entire legacy.
Yeah. It linked macroscopic heat like, the kind of tangible heat you feel radiating from a boiling kettle or a steam engine, to microscopic counting, the literal statistical arrangements of invisible atoms.
Which, we have to remember, was incredibly controversial at the time.
Right, because of the context of the late 19th century.
Exactly. The scientific establishment, led by very influential figures like Ernst Mach, they were strict positivists.
Meaning they only believed in what they could see.
Right. They believed that if you couldn't see something, measure it directly, hold it in your hands, it just didn't belong in serious science.
So atoms were out.
Atoms were considered a convenient mathematical fiction by many top physicists.
Right.
So here comes Boltzmann, claiming that the absolute ironclad laws of thermodynamics and heat are actually just the statistical probability of these invisible bouncing particles.
And he spent his entire career defending that idea. The pushback was brutal, wasn't it?
It was. It wasn't just academic disagreement. It was deeply personal, public humiliation in some cases.
Which is so tragic.
It really is. Boltzmann eventually lost his battle with depression and took his own life in 1906. And this was just a few short years before the physical reality of atoms was definitively proven by people like Einstein and Perrin.
He died defending his statistical formula without ever actually knowing the deepest universal reason why it was the only formula that worked.
It's a profound tragedy in the history of science. I mean, Boltzmann knew his formula accurately described the physical world. He knew the math worked perfectly for steam and gas.
But the underlying universal why was still out of reach.
Right. It was an empirical success without a fundamental philosophical bedrock. But now, we need to abruptly shift the scene.
Let's do it.
We are going to leave the hostility of late 19th century Vienna and jump across the Atlantic to the year 1948.
Okay.
We are walking into the bustling, ozone-scented corridors of Bell Laboratories in New Jersey, and we are looking for a young mathematician named Claude Shannon.
And what a wild departure in character Claude Shannon was from the solemn, tragic figure of Boltzmann.
Oh, completely different universe.
Shannon wasn't studying thermodynamics. He didn't care about heat or steam engines or the physical mechanics of gas molecules.
Not at all.
He was a 32-year-old engineer who was somewhat famous around the Bell Labs campus for riding a unicycle down the long linoleum hallways while simultaneously juggling.
Yeah, he possessed a brilliance that was deeply unconventional and highly playful. If you look at his background, it's fascinating how his mind worked.
Tell us about the telegraph.
Right. So as a kid, growing up in a small rural town in Michigan, he wanted to communicate with his friend down the road. So he built a functioning telegraph system by wiring up the existing barbed wire fences that separated the local farms.
That blows my mind.
Okay.
He just looked at a farm fence and saw a communications network.
Exactly.
Dude.
He was always looking for the fundamental signal buried in the noise. And that way of seeing the world translated directly into his academic career.
He wrote a pretty important thesis, right?
Oh, at the age of 21, he wrote a master's thesis at MIT that is still considered one of the most important single papers in modern engineering.
At 21.
Yeah. He realized that the Boolean algebra he was studying, the abstract logic of true and false, and/or could be mapped perfectly onto the physical electrical relays of a circuit.
Because a switch is either open or closed.
Right. A statement is either true or false. To put that in perspective, he essentially invented the theoretical foundation of all digital circuit design in a master's thesis. And later, during World War II, he worked on classified cryptography, rubbing shoulders with Alan Turing.
So by 1948, this unicycle riding, farm fence telegraphing genius
Yeah.
is trying to solve a very specific modern engineering problem for the phone company.
Yeah, he wants to figure out how to mathematically measure uncertainty in telephone signals.
Right, because if you were sending a voice across a copper wire, there is noise, there is static, there is interference. Shannon wants to know how much pure information is actually traveling down that wire.
Exactly.
And here is the revelation that kicks off our entire journey today. Shannon derives a mathematical formula to measure the average surprise or uncertainty of a message source.
And the formula he derives,
Is identically Boltzmann's formula from the tombstone in Vienna.
it really is.
Okay, let's unpack this. Because a formula designed for boiling water and steam engines matching perfectly with a formula designed for digital telephone signals is either the deepest truth in the universe or the craziest coincidence in the history of math.
What is particularly striking is the method Shannon used to arrive at his formula. He didn't start with complex, esoteric mathematics.
He didn't start with physics at all.
Right. He started with basic, grounded common sense. He asked himself a very philosophical question. He asked, if I want to create a universal mathematical measure of uncertainty, what basic properties must that measure have?
So he laid out 3 simple rules.
3 axioms.
Let me see if I'm tracking this. He just decided what the final math ought to behave like before he even wrote the equations down.
That is the essence of axiomatic thinking.
Yeah.
You build the foundation first. The first axiom he laid down is continuity.
Meaning what, exactly?
In plain terms, this means there are no sudden, violent jumps in your uncertainty. If you change the probability of an event by a tiny, microscopic nudge, your measure of uncertainty should also only change by a tiny, microscopic nudge.
The mathematical curve has to be smooth.
Exactly.
That seems reasonable enough. If the chance of rain tomorrow goes from 50% to 50.1%, my confusion about the weather shouldn't suddenly double. It should just shift a tiny bit.
That's exactly the right way to think about it. The second axiom is monotonicity.
Monotonicity, okay.
This rule dictates that if all possible outcomes of an event are equally likely, then having more possible outcomes means you have more uncertainty.
So if I am flipping a coin, it's 50-50. I have a certain amount of uncertainty. But if I roll a standard 6-sided die, there are 6 equal outcomes. My brain is telling me I am definitely more uncertain about the die roll than the coin flip. Is it really that basic?
It is exactly that basic. A perfectly fair 20-sided die contains more uncertainty than a perfectly fair 6-sided die. More equal choices must equal a higher mathematical value of uncertainty. Shannon demanded his formula reflect that obvious reality.
Makes total sense. What's the third one?
Finally, we have the third axiom, additivity. This is slightly more complex, but it means that if you have 2 completely independent sources of information, their total uncertainty is just the sum of their individual uncertainties.
Give me a visual for that one. What does it mean for them to be independent?
Let's stick with the coins. If I flip a coin in my left hand and you flip a coin in your right hand, the outcome of my coin has absolutely 0 physical influence on the outcome of your coin.
Right.
They are completely separate, independent events. So the total uncertainty we share in the room is just my uncertainty added to your uncertainty. The events don't interact, so the mathematical formulas shouldn't interact in complicated, tangled ways either.
Got it. To make this super relatable for you listening, think about the concept of surprise, like a weather forecast.
Good analogy.
If a meteorologist goes on television and says it is going to be incredibly hot in the Sahara Desert tomorrow, your level of surprise is basically 0.
Because you already knew it.
Right. That message carries very low information because you already knew it was almost certainly going to happen. But if that same meteorologist says it is going to snow 3 feet in the Sahara Desert tomorrow, your surprise is off the charts.
Massive information.
Because the probability of it happening was incredibly low. Shannon wanted to put a hard number on that exact feeling, that average surprise, using just those 3 basic rules: continuity, monotonicity, and additivity.
And this brings us to the mathematical trap.
Ooh, the trap.
Yeah. When you take those 3 incredibly basic common sense rules, and you sit down with a chalkboard and ask what specific mathematical formula can satisfy all three of these conditions at the exact same time, you find yourself backed into a corner.
There aren't many options.
There aren't any other options. In fact, there is exactly one mathematically forced formula.
How does the formula actually work? I know we can't show a chalkboard on an audio deep dive, but what is the machinery of the math he discovered?
It revolves around summing up probabilities and logarithms. Essentially, you look at every possible outcome of an event. You take the probability of that outcome happening, and you multiply it by the logarithm of that probability.
Okay.
Then you just add all those pieces together for every single outcome. The reason logarithms are the secret sauce here is because logarithms possess a unique mathematical superpower. They turn multiplication into addition.
Hold on, why do we need to turn multiplication into addition?
Because of the third axiom, additivity.
Oh, right.
In probability theory, if you want to find the chance of two independent things happening together, like getting heads on a coin and rolling a 6 on a die, you multiply their probabilities.
They multiply them.
But Shannon's rule says we have to add their uncertainties. The only mathematical function in the universe that allows you to take inputs that are multiplying and spit out an answer that is adding is a logarithm.
So the math was dictating its own structure based on those three simple rules.
Yes. The formula is structurally forced. And the mind-bending coincidence is that Shannon's formula, which he derived solely to measure bits of telephone data, is structurally identical to the thermodynamic entropy formula published by Josiah Willard Gibbs in 1902.
Which was a generalization of Boltzmann's work.
Exactly. Gibbs was measuring joules per Kelvin in a physical, tangible system, calculating the heat capacity of gas. Shannon is measuring abstract, non-physical bits of data.
And the core engine of the math is exactly the same function of a probability distribution.
They only differ by a physical constant that scales the units.
There was actually a legendary anecdote about this from 1971. The story goes that Shannon had derived this beautiful new uncertainty formula, but he wasn't sure what to name it.
Right, the von Neumann story.
Yes. So he went down the hall to John von Neumann, one of the most brilliant and intimidating mathematicians of the 20th century, and asked for advice.
And von Neumann gave him some very specific advice.
Supposedly, von Neumann looked at the math and told him, you should call it entropy for two reasons. In the first place, your mathematical function has been used in statistical mechanics under that name. In the second place, and more importantly, nobody knows what entropy really is. So in a debate, you will always have the advantage.
It is a fantastic piece of scientific lore. It perfectly captures the profound mystique and confusion that has always surrounded the word entropy.
It's just a great story.
It is. Now, we should be clear that this specific conversation is highly likely apocryphal. It was recounted decades later by a third party and was never directly confirmed by Shannon himself.
Right.
However, while the conversation might be a myth, the underlying scientific puzzle it points to was very real and very urgent in the mid-20th century. Why do these two completely disparate fields, the physics of heat and the engineering of data, share the exact same structural skeleton?
Which brings us to the very first lock in our sequence of three turning locks. This is the year 1957. A Soviet mathematician named Aleksandr Khinchin steps onto the scene.
Khinchin formally proves the mathematical suspicion we've been discussing. He publishes what is now known as Khinchin's uniqueness theorem.
Okay, the first lock.
He rigorously proves that Shannon's formula isn't just one nice, elegant option among a menu of possible formulas. He proves it is the only mathematical function in existence that satisfies those three common-sense axioms.
Wow.
If you accept continuity, monotonicity, and additivity, you have absolutely no choice. You are forced by the laws of logic into that exact equation.
So the coincidence would actually be if they didn't match.
Exactly.
If physical thermodynamics and digital information theory both require those three basic rules to function, which they absolutely do, then they are on a train track with only one destination. They are forced to arrive in the exact same equation.
That is the implication. Khinchin's theorem is a massive conceptual breakthrough. It answers the structural question of why the formulas match. They match because there is no other formula they could possibly use. However, we have to issue a very stern warning here. This is a load-bearing concept for everything we are going to explore today. Mathematical uniqueness does not equal physical identity.
Meaning, just because they use the same math doesn't mean they are describing the same actual thing in the real world.
Precisely. Let's use a Pythagorean analogy to make this concrete.
Please.
The Pythagorean theorem, a squared plus b squared equals c squared, is a unique fundamental mathematical truth. It works perfectly for calculating the lengths of the sides of a right triangle in geometry.
Basic high school math.
Right. But it also works perfectly in electrical engineering for calculating complex impedance in an alternating current circuit.
Oh, interesting.
They share a unique mathematically forced formula, but drawn triangles on a piece of paper are not physical electrical circuits. They are completely different things that happen to be governed by the same mathematical geometry.
Okay, that makes perfect sense. Khinchin proved there is only one bridge possible between these two ideas.
Yeah.
The math is a forced funnel. But we still don't know if the river flowing underneath is the same on both sides. Uniqueness is necessary to explain why the formulas match, but it is not sufficient to say that abstract information and physical heat are actually, literally, the same thing.
Khinchin gave us the first lock, uniqueness. But to prove that the two fields are physically identical, to prove they are the same river, we need the second lock. We need a bridge theorem.
And remarkably, that bridge arrived in the exact same year, 1957. Independent convergence strikes again. Enter an American physicist named Edwin Jaynes.
Edwin Jaynes published 2 papers in the journal Physical Review in 1957 that essentially shook the philosophical foundations of statistical mechanics.
What did he do?
He did something that most traditional physicists at the time would have considered completely absurd. He started a hardcore physics paper entirely with Shannon's pure abstract information theory. He introduced what is known as the maximum entropy principle.
I want to spend some real time on this because Jaynes's argument is a masterpiece of pure logic. It happens in 5 distinct steps. Can we build a mental model together to walk the listener through this?
Absolutely. Let's do a thought experiment.
Okay.
Step 1. Jaynes says, let's completely ignore physics for a moment. Forget about atoms and heat. Let's just start with Shannon's entropy formula, which Khinchin just proved is the unique mathematical measure of pure uncertainty.
Our perfect yardstick for measuring ignorance.
Exactly. It is our yardstick.
Okay, we have our yardstick of ignorance. Pure math. What is step 2?
Step 2. Now let's look at a physical system. Imagine a perfectly sealed steel box sitting on a table in front of you.
Okay, I'm picturing it.
Inside that box, there is a trillion oxygen molecules bouncing around. You, the human observer, only know a few macroscopic constraints about this box.
Like what?
You have a thermometer, so you can measure its average temperature. You have a ruler, so you can measure its total volume. But you are completely, hopelessly blind to the microscopic details.
I can't see the atom.
Right. You have absolutely no idea what the speed, direction, or position of molecule number 4 billion is at any given nanosecond.
Which is the reality of all everyday physics. I can measure the temperature of my living room, but I can't track every single oxygen molecule hitting the walls.
Exactly.
So I have some hard knowledge, but a massive amount of ignorance.
What does Jaynes do in step 3?
Step 3 is where Jaynes introduces the brilliant philosophical pivot. He says, as a physicist, you need to assign mathematical probabilities to all those unknown microscopic states to predict how the gas will behave.
But how do you do it without just making stuff up?
That's the genius of it. You must assign the probabilities in a way that maximizes Shannon's uncertainty formula, while strictly obeying the macroscopic constraints you actually measured, like the temperature.
So you are intentionally making yourself as uncertain as mathematically possible, while still respecting the few things you know for sure.
It's like saying, I know the average height of people in this room is 5'9", but beyond that, I am going to assume absolute maximum randomness about who is actually standing where.
Precisely.
It is intellectual honesty encoded as a mathematical procedure. You refuse to pretend to know what you don't know.
It is the ultimate expression of epistemological modesty. Be maximally non-committal about everything you haven't directly measured. And that philosophy leads directly to step 4, the mathematical revelation.
The payoff.
When you actually perform this calculation, when you maximize Shannon's pure information entropy subject to the physical constraint of average energy, the famous Boltzmann distribution falls out perfectly on the chalkboard.
The exact equation that governs equilibrium statistical mechanics.
Yes.
The very thing Boltzmann spent his life trying to explain, the thing he died over, it just organically drops out of pure information theory mixed with intellectual honesty.
It drops out completely unforced by physical assumptions. Nobody assumed the Boltzmann distribution from the start. Nobody programmed in the mechanics of colliding spheres.
It just happens.
It is mathematically forced purely by the process of rational inference. And that brings us to step 5, the re-identifications. Because the Boltzmann distribution falls out naturally, absolutely everything else in thermodynamics follows right behind it. All the laws of heat, pressure, and chemical reactions emerge from the math of information.
And this leads to some radical reinterpretations of how we view the universe, doesn't it? Things that we thought were fundamental physical properties suddenly look very different under this light.
Very different. Let's take temperature as the primary example.
Okay.
We typically think of temperature as a fundamental, tangible property of the physical universe, something that exists out there in the world.
Right.
But under Jaynes's information framework, temperature isn't a fundamental property at all. It is what mathematicians call a Lagrange multiplier.
A Lagrange multiplier. That sounds intimidating. How do we visualize that without a math degree?
Think of it as a penalty weight or a bookkeeping device.
A bookkeeping device.
Yeah. When you are doing optimization math-like, trying to maximize uncertainty, but you have a strict rule you can't break, like the total energy of the box, you need a mathematical parameter that connects the two. You need a variable that tracks how tightly your hard rule is restricting your randomness.
Okay, I'm following.
Jaynes is saying that temperature is just that bookkeeping device. It tracks how tightly your macroscopic measurement of energy is constraining the possible microscopic realities of those molecules.
It's wild. Temperature is a bookkeeping device for human ignorance.
Yes.
If we knew the exact position and speed of every molecule, we wouldn't need the concept of temperature at all, because we'd have zero uncertainty.
Precisely.
And if that's true, it means the second law of thermodynamics. The absolute rule that entropy must always increase, that things degrade into disorder, that coffee cools down gets reinterpreted too.
Yes, the second law becomes a theorem about rational inference. It essentially states that you cannot learn more about a system by observing less of it. When a physical system coarse grains, your uncertainty must increase.
Wait, define coarse graining for us. What does it mean for a system to coarse grain?
Imagine looking at a highly detailed digital photograph on your computer screen. You can see every single pixel, every sharp line.
Okay.
Now imagine taking a step back and applying a heavy blur filter to the image. The sharp pixels bleed together into larger, blurry blocks of color. You have lost the microscopic detail. You have coarse-grained the image.
Ah, I see.
In physics, when a drop of ink disperses in a glass of water, the initially sharp, distinct boundaries of the ink drop blur out into the water. The microscopic details become scrambled. The system has coarse-grained.
Right, it gets blurry.
And when details blur together, your uncertainty about where any specific ink molecule is must increase. Statistical mechanics isn't just a physics theory that happens to use probability. Statistical mechanics is probability theory applied directly to physics.
Okay, I'm going to stop you right there, and I'm going to put on my skeptic's hat.
Go for it.
Because I can hear the natural pushback from traditional physicists, and honestly, it makes a lot of intuitive sense.
Let's hear the objection.
Ice melts in an empty room, whether or not anyone is watching it. A gas expands into a vacuum, regardless of whether a human being is sitting there doing math about it.
Sure.
The physical world does not care about my state of belief, my uncertainty, or my rational inference. The physical world just is.
Right.
How can Jaynes claim that thermodynamics, real physical heat and energy, is just a method of information processing? It sounds like he is saying human consciousness creates thermodynamics.
It is a vital objection, and it is the exact pushback that caused intense controversy around Jaynes's work for decades. Physicists hated the idea that a subjective observer was somehow smuggled into the objective laws of steam engines.
It feels like a cheat.
But here is how Jaynes resolved it, and it requires careful philosophical footing. You have to cleanly separate the constraints from the method.
The constraints from the method are...
The physics in the box is entirely real and objective. The total energy in the box of gas is real. The number of particles is real. The volume of the steel box is real. Those are the physical constraints. The ice melting is driven entirely by those objective physical constraints. What Jaynes is arguing is that the information theory doesn't replace the physical reality. Rather, it provides the only logically consistent method for how we reason from those microscopic physical constraints to the macroscopic outcome we observe.
I see.
The physics provides the absolute ground truth. The information theory is the engine of the mathematics. The inference interpretation fully contains the objective physics. It absolutely doesn't replace it with human psychology.
Let me see if I have this. The subjective part is just the mathematical tool we use to calculate the blurriness, but the inputs driving the blurriness, the actual collisions of molecules, are hard, objective reality.
Exactly. The map is subjective, but the territory is real. And this leads us to something incredibly profound. I want to connect this directly to a massive concept that we explored in a previous deep dive. Do you remember our discussion on the data processing inequality, or the DPI?
Hold on. The data processing thing from that deep dive a few months back. You were talking about the rule governing biological systems, right? Like how cell signaling and neural transmissions work in the brain.
That is the one.
If I recall correctly, the rule basically states that as a signal moves through a system, whether it's a neuron firing across a synapse or a cell communicating with another cell, the processing of that data can only degrade the quality of the information.
Yes.
It can never miraculously create new, clearer information out of nowhere. A copy of a copy is always slightly worse.
That is a perfect summary. The data processing inequality is a cornerstone of information theory. It states that processing data destroys information. Now, bring Jaynes' bridge theorem into this. If information entropy and thermodynamic entropy are mathematically identical...
Wait, are you saying the DPI from biological cell signaling is literally the second law of thermodynamics?
Yes, they are the exact same theorem wearing different clothes. When a biological system processes data, it inevitably destroys some information due to noise. When a physical system evolves over time in coarse grains, it increases your uncertainty.
Processing destroys information. Coarse graining increases uncertainty. Entropy strictly increases.
Those are three different vocabularies expressing the exact same fundamental truth about how the universe operates.
That is absolutely staggering. The mathematical rule that dictates why a highly compressed audio file on your phone sounds slightly worse than the original studio recording is the exact same mathematical rule that dictates why ice melts on a hot sidewalk and why the entire universe is slowly marching toward thermal equilibrium.
It is the ultimate unification of abstract information and physical reality. But as beautiful and mathematically perfect as Jaynes' bridge is, we are still missing the final, most crucial piece of the puzzle.
There's more.
Oh yeah. A mathematical bridge, even a perfect one, is still just theory on a chalkboard. If this unification is truly physically real, it has to be able to solve a real, tangible physical problem that has stumped scientists.
It needs a test.
It must slay the longest-running, most stubborn thought experiment in the history of physics.
Oh, this is where the story gets incredibly good. We are talking about the 115-year ghost, Maxwell's demon.
Introduced by the brilliant Scottish physicist James Clerk Maxwell in 1867. To understand the stakes here, we need to set the stage for the listener in vivid detail. Let's go back to our theater of the mind.
Okay, painting the picture.
Imagine a large glass box filled with gas. The gas is all at one uniform, lukewarm temperature. Now imagine a solid, impenetrable wall dividing that box right down the middle into a left chamber and a right chamber.
Right.
Right in the very center of that wall is a tiny microscopic door.
And hovering right next to that tiny door is the demon, a hypothetical, microscopic, intelligent being. And this demon has one very specific, tedious job.
It watches the gas molecules bouncing around in both chambers.
Right. If it sees a really fast, highly energetic, hot molecule coming toward the door from the left side, it quickly slides the door open and lets it pass into the right chamber.
And if it sees a slow, sluggish, cold molecule coming from the right side, it opens the door and lets it pass into the left chamber.
And remember, the door is perfectly frictionless and weightless. Opening and closing it requires essentially zero physical energy. So what happens over time?
If the demon sits there and does this long enough, continually sorting the molecules, all the fast, hot molecules end up trapped on the right side. And all the slow, cold molecules end up trapped on the left side.
Which means one side of the box becomes boiling hot and the other side becomes freezing cold.
And that is the paradox that terrified physicists for a century, because doing that directly blatantly violates the second law of thermodynamics. The second law says that heat naturally flows from hot to cold until everything is a uniform, lukewarm mush. It says entropy always increases. But the demon took a uniform mush and separated it into hot and cold.
It decreased the entropy.
It decreased the entropy of the system, and it did it without expending any physical energy to pump the heat. It reversed the natural flow of the universe just by sorting. If Maxwell's demon can exist, even in theory, then the second law is broken.
And if the second law is broken, all of modern physics collapses.
Entirely.
Physics spent over a century trying to exorcise this demon, desperately trying to prove why it couldn't work. And there were three major, highly publicized failed attempts before the final solution. Let's run through those failures because they show just how fiendishly hard this problem was.
They do.
The first major attempt was in 1912 by a Polish physicist named Marian Smoluchowski. He tried to get rid of the intelligent demon and build a mechanical trapdoor.
Right. Smolakowsky reasoned that an intelligent being is too complex to model, so he said, let's replace the demon with a tiny, spring-loaded, one-way trapdoor.
Right.
The spring is stiff enough that only the fast, high-energy molecules hitting it have enough force to bump it open and pass through. The slow molecules just bounce off. It sorts the gas automatically.
Seems like a good solution.
But Smolakowsky was a brilliant enough physicist to realize his own invention would ultimately fail.
Why does a spring-loaded door fail?
Because the trapdoor itself is a physical object. It is made of atoms. As it sits there, getting battered by thousands of molecules, it absorbs some of their kinetic energy. It starts to heat up.
Oh, see.
And at a microscopic level, heat is just movement. The door begins to physically vibrate and jiggle with thermal fluctuations. Eventually, it jiggles so violently that it just flaps open and close completely at random, letting both fast and slow molecules pass both ways.
So the heat defeats the mechanical sorting mechanism.
Exactly.
But that didn't kill the paradox because it leaves a massive loophole. What if the demon isn't a mechanical spring? What if it's a truly intelligent being that doesn't rely on physical gears and springs that can overheat?
Which brings us to 1929 and the Hungarian-American physicist Leo Szilard.
Ah, the second exorcism.
Szilard completely stripped down the experiment to its absolute theoretical minimum, a single-molecule engine. He calculated that an intelligent demon must expend some entropy to operate.
So he found a cost.
He even got the exact numerical cost of the entropy right. He calculated it as the Boltzmann constant times temperature times the natural logarithm of 2.
But he got something wrong.
He misidentified where that tax was being paid. He attributed this entropy cost to the act of measurement. He argued that the demon pays the physical energy tax the exact moment it looks at the molecule to measure its speed.
He essentially said that gathering information about the world requires physical work. But that turned out to be wrong, too.
It did, though it took decades for the scientific community to realize the flaw in his logic. Before the fatal flaw in Szilard's argument was exposed, there was a third major attempt to kill the demon in 1951 by a French physicist named Léon Brillouin.
Attempt number 3.
Brillouin tried to get highly specific about Szilard's measurement problem. He argued that to see the molecules in a dark box, the demon would need a flashlight.
A microscopic flashlight.
Right. It would need to shoot photons at the molecules to illuminate them, and generating those photons requires physical energy, which produces entropy, which pays the thermodynamic tax.
But even as a non-physicist, that feels like a cheat to me. Because it only disproves one very specific human-centric method of sight.
Exactly.
What if the demon is blind, but feels the molecules through sonar? What if it senses their electromagnetic fields? Brillouin didn't kill the fundamental concept of the demon. He just took away its theoretical flashlight.
You've hit the nail on the head. It was an incomplete exorcism, 3 major attempts, 3 failures. The demon survived.
Damn.
But if Jaynes's bridge theorem is correct and abstract information is thermodynamics, then the demon must fail for a purely information theoretic reason.
Not because of a jiggling spring, and not because of a hypothetical flashlight.
Exactly. If information and heat are the same thing, we need a novel prediction about how information behaves physically.
Which brings us to the third lock. The physical consequence.
The year is 1961, and we are wandering the halls of an IBM research facility with a physicist named Rolf Landauer. Landauer was deeply interested in the physical limits of computing. He started asking a question that seemed almost ridiculously philosophical at the time. What is the absolute minimum physical energy required to perform a computational operation?
We have to remember the context here. Computers in 1961 were the size of a room.
Huge machines.
They used vacuum tubes and huge magnetic tape reels. They consumed massive amounts of electricity just to turn on. So the idea of calculating the absolute minimum physical energy of a tiny computation was wildly abstract.
It was visionary. But Landauer presses forward, and he proves something astonishing. He shows mathematically that if information is indeed physical, then whenever you reduce the number of possible microscopic states of a system, you are decreasing its information entropy.
And the universe has a strict rule about decreasing entropy.
Let me try to make that concrete for the listener. Imagine a single computer memory bit. It can be a 1 or a 0. That is 2 possible states.
Right.
If you want to erase that bit, if you want to force it to be a 0 no matter what it was before, wiping the memory clean, you have forcefully reduced the possibilities from 2 states down to 1 state. You have destroyed information.
You have decreased the uncertainty.
And because Jaynes proved that information entropy is thermodynamic entropy, Landauer realizes a profound truth. The universe will not let you destroy that entropy for free. It cannot simply vanish into nothingness.
The ledger have to balance.
The second law of thermodynamics demands that if the entropy of the computer bit goes down, the entropy of the surrounding universe must go up to compensate.
And the universe demands that payment in a very specific currency. It demands physical heat.
Exactly. Landauer calculates the exact universal prediction. Erasing a single bit of information costs an absolute minimum of physical heat energy.
And what's the formula?
The formula he derives for that heat cost is the Boltzmann constant times the ambient temperature times the natural logarithm of 2.
The same number Szilard found?
The exact same number. It is an unimaginably tiny number, but crucially, it is not zero. It is a hard, inescapable physical limit woven into the very fabric of reality.
That is Landauer's principle. The physical cost of erasure. Forgetting is not free. And this brilliant realization sets the stage for the ultimate final resolution of Maxwell's demon.
Finally.
The year is 1982. Another physicist at IBM, Charles Bennett, takes Landauer's principle and finally drives a theoretical stake through the demon's heart.
Bennett does this by making a crucial, brilliant correction to the work of Szilard and Brillouin.
Yeah.
Remember, they thought the demon paid the energy tax when it measured the molecule.
Right.
Bennett rigorously proves they were wrong. He proves that measurement is thermodynamically free. You can observe a molecule, compute its trajectory, and sort it left or right, all without paying a single drop of entropy tax to the universe.
So looking is free.
Computation and observation in a perfectly reversible system do not violate the second law.
Wait, hold on. If the demon can look at the molecules for free, and he can slide the weightless door for free, why does it fail? How does the universe stop it from breaking the second law?
Because the demon is an intelligent entity, which means it must have a memory. And every physical memory is finite. Every single time the demon looks at a molecule, it has to record a bit of information in its microscopic brain. Molecule 400 is fast, it went left. Molecule 401 is slow, it went right.
So it's storing data.
As it sorts millions of molecules, its memory banks start to fill up.
Oh, I see the trap closing.
Eventually, to keep sorting the gas, the demon runs out of space. It has to clear its memory. It has to erase the old information to make room for new observations.
And what did Landauer prove about erasing information?
That erasing information physically costs heat.
Yes. The demon fails because it cannot forget for free. The thermodynamic cost isn't in looking at the molecules. The cost is in erasing the data.
The exact moment the demon wipes its memory drive to continue working, Landauer's principle kicks in. The demon physically radiates heat into the gas.
And the amount of heat it radiates perfectly exactly replaces all the entropy it had previously sorted out of the system.
The ledger is balanced. The second law is saved.
That is just breathtaking. The demon fails because it can't forget for free. Think about the chain of human genius required to figure that out.
It's remarkable.
It took 115 years and 6 different brilliant scientists passing the baton across generations. Maxwell invents the demon in 1867. Smolakowski shows the mechanical problems with the trapdoor. Szilard finds the mathematical cost, but incorrectly points at measurement.
Shannon defines the mathematics of information.
Jaynes bridges information to physical thermodynamics. Landauer discovers the physical cost of erasure, and Bennett finally uses the cost of erasure to kill the demon. Every single one of them fundamentally require the work of the person before them to make the next leap.
It is arguably one of the most beautiful, intricate arcs in the entire history of science. But as empirical scientists, we must ask the final, rigorous question.
Did they ever prove it in a lab?
Landauer's principle, the idea that erasing an abstract bit physically creates heat, was a theoretical prediction made on paper in 1961. Was it ever actually proven in a physical laboratory?
And it was. But it took decades of technological advancement to build instruments sensitive enough to measure it. We are now jumping forward to the year 2012 in a laboratory in Lyon, France. A physicist named Antoine Bérout sets up one of the most delicate, microscopically precise experiments ever conceived to test this exact theory.
Bérout and his research team needed to create a literal physical computer bit that they could manipulate.
What did they use?
They took a microscopic silica glass bead, suspended it in a liquid solution, and trapped it using a highly focused optical laser. They shaped the laser field to create what is called a double well potential.
A double well potential.
Imagine an invisible microscopic landscape shaped like a W. The glass bead can sit in the left valley of the W, which represents a state of 0, or it can be bumped over the middle ridge into the right valley, which represents a state of 1.
So it is quite literally a physical memory drive made of one single microscopic bead of glass hovering in water.
Precisely. And then the critical step, they erased the bit.
Ow.
They forced the bead into the 0 valley regardless of whether it started in the 0 or the 1. They did this by slightly adjusting the laser, essentially tilting the microscopic landscape, forcing the bead to roll downhill into the 0 state.
They destroyed the uncertainty. They erased the information.
And then they measured the heat released by that single glass bead into the surrounding water.
And what did they find?
They measured it with astonishing precision, and what they found was a triumph of theoretical physics. They found that as they performed the erasure more and more efficiently, doing it as slowly and carefully as possible, the heat dissipated into the water approached an absolute hard limit.
It never dropped below it.
It never, ever dropped below it. And that limit was precisely Landauer's mathematical prediction. The Boltzmann constant times temperature times the natural logarithm of 2.
That gives me chills. 2012. It was definitively proven in reality.
Yeah.
But there is a deeply poignant historical parallel here that we have to acknowledge.
Yes, regarding Landauer.
Rolf Landauer, the visionary who predicted this fundamental physical law in 1961, passed away in 1999. He missed seeing his life's greatest work confirmed in the lab by exactly 13 years.
Which echoes Boltzmann.
Just like Ludwig Boltzmann, who died in 1906, just a few short years before the physical reality of atoms was definitively proven, which would have fully validated his tombstone formula.
It is a sobering reminder that science is a generational relay race. You are handed the baton, you run your leg as hard as you can, but you don't always get to see the finish line. You have to trust the process.
If you step back and look at what we've covered today, it's actually staggering. I want to walk through this deliberate sufficiency inventory with you, because we didn't just find a coincidental math formula. We have 3 distinct turning locks, and none of them work alone.
Let's lay them out.
Okay, the first lock.
The first lock is Khinchin's uniqueness theorem. Khinchin proved the mathematical structure is absolutely forced. There is no other way to measure uncertainty. But as we established with the Pythagorean analogy, unique math isn't physics.
Triangles aren't circuits.
Right. It's just an interesting mathematical coincidence on its own.
Until Jaynes comes along with the second lock, the bridge theorem. Jaynes proves that the physics matches the math perfectly. Thermodynamic entropy is just information entropy applied to physical constraints.
But even then, if we stop at Jaynes, critics can argue that it's just a clever mathematical rewriting trick, a subjective philosophical way of doing statistics that doesn't generate any new physical phenomena.
A bridge theorem without a novel prediction is just philosophy.
Exactly, which is why the third lock is the master key. Landauer and Bennett predicting, and Baruch physically proving, that forgetting costs energy.
The physical consequence.
They demonstrated a tangible, measurable physical consequence, the heat cost of erasure, that neither pure information theory nor traditional thermodynamics could have predicted completely on their own.
When you have all 3, uniqueness of the mathematics, the bridge theorem of identity, and a confirmed novel physical prediction, the debate is over.
It is.
This isn't an allegory anymore. It isn't a clever metaphor about telephone wires and steam engines. It is a fundamental law of nature. Information and physical thermodynamics are inextricably the exact same thing at the deepest level of reality.
Yeah.
Here's where it gets really interesting, because the story isn't over. Science never stops at the horizon.
It doesn't. The unification is beautifully complete for thermodynamics and information, but the frontier is always expanding. Now, theoretical physicists are looking at gravity.
Oh, wow.
In the 1970s, Jacob Bekenstein and Stephen Hawking demonstrated mathematically that black holes also possess entropy, and that entropy is proportional to the surface area of the black hole's event horizon.
So the bridge theorem is still going.
The bridge theorem is currently in progress out there in the cosmos, trying to link quantum information theory, thermodynamics, and the crushing gravity of a black hole. We're trying to find out if space-time itself is built out of information.
What an incredible, sprawling journey. Think about the timeline we just walked through together. 147 years of human inquiry.
A long road.
From Rudolf Clausius first coining the word entropy in the 1860s, to Boltzmann fighting a lonely war for the statistical formula, to Shannon finding that exact same formula hidden in telephone wires, to Jaynes building the philosophical bridge, to Landauer predicting the heat of a digital bit, all the way to Baruch measuring the physical cost of a glass bead forgetting in 2012.
It is a towering triumph of the scientific method, and it leaves us with an ultimate takeaway that is profound in its simplicity. Information has physical weight, and forgetting costs physical energy.
I want to leave you with a final provocative thought to mull over as you go about your day. We've just spent an hour proving that if the universe strictly enforces a physical energy tax every single time a tiny microscopic system clears its memory, what does that imply about us? Think about the sheer volume of information you consume, process, and discard every single day in our hyper-connected digital world. You are scrolling, reading, watching, filtering, and constantly overwriting your short-term memory at a pace humans have never experienced before. If forgetting fundamentally physically costs energy at the deepest levels of physics, perhaps the overwhelming mental exhaustion we feel from modern information overload isn't just a psychological metaphor. Maybe it is the second law of thermodynamics, literally and physically collecting its inevitable tax on your brain. Until next time on The Deep Dive.